Alright, in this video we're going to be looking at section 5.7. We're going to be looking at the change of variables in multiple integrals. And so we're going to start out with an example here. We're going to want to evaluate the double integral over the region R of x minus y over x plus y dA. For the region R bounded by x minus y equals 0, x minus y equals 1, x plus y equals 1, and x plus y is equal to 3. So let's go ahead and sketch this. So y is equal to x, and that would be y is equal to x minus 1 if we were to solve for y in each one of those. So we have two parallel lines there. All right. And then x plus y is equal to 1. That'd be y equals 1 minus x. And then the other one would be y is equal to 3 minus x. So again, another set of parallel lines. Okay, and so the region that we're looking at is this region right here. So if we were going to use our ordinary measure or ordinary strategies for integrating this, we'd have one integral there, 2, and 3, because the upper or the lower function changes. Okay, so the first one there, and then we have a change in the lower function, and we have a change in the upper function. So that's going to require 3 double integrals. If we go the other way, all right, there's 1, and then we'd have a change in the lower or the left function, and then we'd have a change in the right function or the upper function. So this is going to require 3 double integrals either way, and we want to see if there's a way to make the integration a little bit easier so we don't have to use 3 double integrals. So we're going to look at, maybe we can do some sort of substitution or something like that. So if we look at this integral from Cal 1, the integral of x squared times quantity 2x cubed minus 5 to the 4th power dx, which we would have done in Cal 1. So we said, well, let u be the 2x cubed minus 5, then differential du is going to be equal to 6x squared dx. Don't forget the dx. And so we want to get a good match there, so we can introduce a factor of 6, and then we need to offset that factor of 6 by introducing a factor of 1/6. So those will absorb, and so we'll just have the 1/6 out in the front, and we'll be left with the integral of u to the 4th du, and so we're going to have 1/6 u to the 5th over 5 plus the constant of integration. So that's going to be 1 over 30 times the quantity 2x cubed minus 5, and that quantity there to the 5th power, and then plus your constant of integration. So we have another type of substitution that we're going to use here on the next slide. It says, so going back to the u substitution, consider the integral from a to b of f of x dx, and suppose that x is equal to g of u, then dx is equal to g prime of u du. If a is equal to g of c and b is equal to g of d, then the integral from a to b of f of x dx is equal to the integral from g of c to g of d of f of g of u times g prime of u du. And so this would be your u substitution with a change of variables. And so the last example we did is similar to this, other than we didn't have a definite integral. So the g of c and the g of d are going to be your change of variables. Okay? All right. So let's look at change of variables for double integrals. Okay? And make one is we actually kind of started on this direction and we worked our way backwards. Okay. All right, so let's look at our change of variables for double integrals, the Jacobian. So if x is equal to g of uv and y is equal to h of uv, then the Jacobian of x and y with respect to u and v is the partial derivative of x comma y with respect to the partial derivative of uv, and then we set up this little matrix that we're going to set up to find the determinant of a 2 by 2 matrix. So it's going to be row 1 is going to be partial of x with respect to u, partial of x with respect to v, partial of y with respect to u, and partial of y with respect to v. So when we find the cross product of that, we're going to have dx du times dy dv minus dy du times dx dv. For a region R that is vertically or horizontally simple in the xy plane, and let S be a vertically or horizontally simple region in a UV plane, let T from S to R be given by T of UV is equal to x comma y, which is equal to G of UV comma H of UV, where G and H have continuous first partial derivatives. Assume that T is a one-to-one function except possibly at the boundary of S. If f is continuous on R and the Jacobian is not equal to 0 on S, then what we can do is we can replace the double integral of the region R of f of x, y, dx, dy with the double integral over the region S of f of g of uv comma h of uv, so yes, which we're going to replace our x and y's with, times the absolute value of the Jacobian, and then du dv. So we're going to take a look at a couple examples of applying this. So let's go back and revisit that first problem. So we wanted to evaluate the double integral over the region R of x minus y over x plus y dA for the region R bounded by x minus y equals 0, x minus y equals 1, x plus y equals 1, and x plus y is equal to 3. So we're going to go ahead and sketch that same region. Okay. And so this would be our region R right here. All right. And we had mentioned earlier that that's going to take 3 double integrals to evaluate this integral. So what we're going to do here is notice that we have x minus y equals 0 and x minus y is equal to 1. So we're going to introduce the variable u to be equal to x minus y. Okay, so then u is going to be equal to 0 and u is equal to 1. That's where x minus y is equal to 0 and x minus y is equal to 1. We're going to let v equal x plus y, and so x plus y is equal to 1, x plus y is equal to 3, gives us the 1 and the 3. And so now our region S, we have converted from the xy plane, we have done a transformation over to the UV plane. Alright, and so this is now our region S, okay? And so this is going to be easier to work with. So usually we take some sort of region like I have above, a parallelogram, and we convert it into a rectangle that's going to be a lot easier. I think there's an example or two in the homework where you take an ellipse and you convert it into a circle, which is going to be easier to work with. Okay, so let's go through and keep working on this. So u is equal to x minus y, v is equal to x plus y, and we need to solve for x and y in terms of u and v because we need that for our Jacobian. Alright, so u plus v is equal to 2x, notice the y's would absorb, so you can divide or multiply by 1/2, and so you have half of u plus v is equal to x. So the partial derivative of x with respect to u is going to be 1/2. Partial derivative of x with respect to v is going to also be 1/2. Alright, now let's take u is equal to x minus y and subtract from it v, which is equal to x plus y. So you'd have u minus v, and then x minus x absorbs, and negative y minus y would be a minus 2y. Okay, then we can divide by a negative 1/2 and distribute the negative signs, so that give us 1/2 v minus u is equal to y. partial derivative of y with respect to u is going to be negative 1/2. Partial derivative of y with respect to v is also going to be 1/2. Okay. So let's go ahead and write out our Jacobian. So the partial derivative of xy with respect to u and v. Okay, first column, first row. Oh, well, it looks like we're doing column here. So first column is going to be dx du, and then dy du. And second column dx dv, and dy dv. Okay, so it's going to be equal to 1/2 minus 1/2, 1/2, and 1/2. And then we're going to go ahead and take the determinant of this. So 1/2 times 1/2, and then minus negative 1/2 times 1/2. So what we're going to get is 1/4 plus 1/4, which is 2/4, and that reduces to 1/2. Okay, and that's our Jacobian. Now when we look at the double integral over the region R of x minus y over x plus y dA, that's going to be equal to, it would be the double integral over the region S of x minus y would be u, x plus y would be v, and then we can do du dv. Okay. So the limits for v is 1 to 3. The limits for u would be 0 to 1. And then x minus y is u, x plus y is v, du dv. It's going to be equal to the integral from 1 to 3 of u squared over 2 times 1 over v, evaluating u from 1 to 0 du. So when we evaluate the u from 0 to 1, that's just going to give us a 1 squared over 2 minus a 0 squared over 2, which is going to be 1/2. We'll slide the 1/2 out. We have the integral from 1 to 3 of dv over v, which is going to equal to 1/2 ln absolute value of v. We're going to evaluate v from 1 to 3. So we have 1/2 times the quantity ln absolute value of 3 minus ln absolute value of 1, which is just going to be equal to the 1/2 ln of 3. The natural log of 1 is going to be 0. Okay. All right, let's go ahead and look at it. I think we got 2 more examples planned in this video. So let's go ahead and look at the next one here. So next one here, we have the double integral over the region R of x minus 2y over x plus y dA. And the region is x minus 2y is equal to 1, x minus 2y is equal to 4, 2x plus y is equal to 1, and 2x plus y is equal to 3. If we sketch this, we're also going to get another parallelogram. So here would be what you're looking at, and we can go ahead and fill this in real quick. So this would be your region R, okay? And so what we want to do is we want to use our change of variables so that we can have a simpler object to work with. Okay, so let's take this off. All right. So notice that we have x minus 2y is equal to 1 and x minus 2y is equal to 4. So we can go ahead and call that u. So u is going to be equal to x minus 2y. So then x minus 2y is equal to 1 and 4, so that gives us our limits. And then we're also going to let v equal 2x plus y. So then that's going to give us y is equal to 1 and 3. And sorry, it wouldn't be y. That's the wrong variable. That should be v. All right. So let's go ahead and sketch our UV plane and then this object that we're looking at. So from on U we're going 1 to 4, on V we're looking at 1 to 3. So we're looking at another rectangular region, and this would be our region S. Okay, so this would be our region S. Alright, so now what we need to do is we need to solve for X and Y in terms of U and V, and we do this so we can get the Jacobian. So if we simply add U and 2V, 2v is equal to 4x plus 2y. So when we add those, we'll have u plus 2v is equal to 5x, and then the purpose of this was to get the y's to absorb. So then x is equal to 1/5 u plus 2v. So then differential of x with respect to u is going to be 1/5. Differential of x with respect to v is going to be 2/5. Okay, so now what we want to do is we want to eliminate the x, so we can solve for y in terms of u and v. So if we multiply u by -2, that's going to be -2x plus 4y, and then we're going to add that to v, which is equal to 2x plus y. So by construction, the x's are going to absorb, and we have v minus 2u is equal to 5y. So then y is equal to 1/5 times v minus 2u. Partial of y with respect to u is going to be -2/5, and the partial of y with respect to v is going to be 1/5. All right, so then if we want to find the Jacobian, the partial of xy with respect to uv, okay, so partial of x with respect to u, partial of y with respect to u. Okay, so there's column 1. Column 2 would be partial of x with respect to v, and partial of y with respect to v. Okay, all right, so this is going to be 1/5, and then -2/5, 2/5, and 1/5. All right, so then we're going to do 1/5 times 1/5, which is 1/25, and then minus -2/5 times 2/5, which is going to be 4/25. So that's going to give us 5/25, which is equal to 1/5. And then, of course, with the Jacobian, we usually put the absolute value on it. We don't need it here because the 1/5 is positive. Okay? All right, so our double integral over the region R of x minus 2y over 2x plus y dA is equal to, and so we'll do the order, we'll do du first and then dv. So dv is going to be the outer integral, so it's going to be from 1 to 3. Du will be 1 to 4 is the limits of integration. X minus 2y is u, and 2x plus y is v. Don't forget your Jacobian of 1/5 du dv, and this is essentially the same integral as we had as the previous problem. So we'll slide out the 1/5. We'll go ahead and integrate also. So you have the integral from 1 to 3. Integral of u is u squared over 2 times 1 over v. Evaluating u from 1 to 4 dv, excuse me. So we have 1/5, and then we're going to have 4 squared over 2 minus 1 squared over 2, and then that's going to be times 1 over v. So the 4 squared over 2 minus 1 squared over 2 is a constant, so we can go ahead and factor that out. And then what we have left is the integral from 1 to 3 of dv over v. All right, so now we have 16 minus 1 over 10. Natural log, not of x, that's the wrong variable. Should be v. Natural log absolute value of v, and we're going to evaluate that from 1 to 3. So it's going to be 15 over 10 times the natural log of the absolute value of 3 minus the natural log of the absolute value of 1. So we're going to 15 over 10 reduces to 3 halves. Natural log of 3, where the natural log of 1 is 0, so that just goes away. You don't need the absolute value bars on the 3 because it's already positive. All right, and we got one more example in this video, so hang in there. Okay, so this last integral we're going to be looking at, a double integral, is the double integral over the region R of e to the xy dA. Region R is going to be y equals x over 2, y equals x, y equals 1 over x, and y is equal to 2 over x. We'll also assume that x and y are greater than 0, so we'll only be looking in quadrant 1. So let's go ahead and sketch our region R. So we have the identity y equals x. We have the other line y equals x over 2. We have the reciprocal function y equals 2 over x. And we have the reciprocal function y over x. sorry, 1 over x, not y over x, 1 over x. And then there's our region R. So it's not a parallelogram, but we can still straighten this out and make this into a rectangular region. So if I take the first equation and I divide by x, I'd have y over x is equal to 1/2. If I take the second equation, y equals x, and divide by x, I'll have y over x is equal to 1. Okay, and I'm doing this because I want the x and the y to be on the same side of the equation. Okay, if I take y equals 1 over x, I can multiply by x and get yx is equal to 1. And y is equal to 2 over x, multiply by x, so you have yx is equal to 2. All right, so u is going to be a function of x and y, so u will let be y over x. Okay, so then we can see our limits would be 1/2 to 1 for the u. So we look at our changing coordinate systems here, the UV plane. And u is going from 1/2 to 1. Now we're going to let the v equal xy or yx. So xy or yx is going from 1 to 2. So again, we're looking at a rectangular region here, and that is our region S. All right. Now for the Jacobian, we need to solve for x and y in terms of u and v. So if we take u equals y over x and multiply by x, we have ux is equal to y, and we have v is equal to xy. If we divide v is equal to xy by x, we have v over x is equal to y. So they're equal to y, so they're equal to each other. So ux is equal to y, v over x is equal to y, so u times x is equal to v over x. Okay, multiply by x on both sides and divide by u, so you have x squared is equal to v over u. Take the square roots, and normally we get a plus or minus, but because the x and y is positive, the u and v is positive, we won't have a plus or minus. So we're going to have the square root of v over the square root of u, which we can rewrite as v to the 1/2 times u to the minus 1/2. Partial of x with respect to u is going to be negative 1/2, v to the 1/2, u to the negative 3/2. Partial of x with respect to v is equal to 1/2 v to the minus 1/2, u to the minus 1/2. All right. Now y is equal to v over x, and x we determined was v to the 1/2, u to the negative 1/2. So this means that y is equal to v to the 1/2, u to the 1/2. So partial of y with respect to u is going to be 1/2 v to the 1/2, u to the negative 1/2. Partial of y with respect to v is going to be 1/2 v to the negative 1/2, u to the 1/2. So let's go do our Jacobian. So the partial of xy with respect to uv, we'll set up our matrix. So it's partial of x with respect to u, partial of y with respect to u for column 1, partial of x with respect to v, and partial of y with respect to v for the second column. All right, so dx du is negative 1/2 v to the 1/2, u to the negative 3/2. Partial of y with respect to u is 1/2 v to the negative 1/2. V to the 1/2, u to the negative 1/2. Partial of x with respect to v is 1/2 v to the negative 1/2, u to the negative 1/2. And lastly, partial of y with respect to v is going to be 1/2 u to the negative 1/2. Sorry, I might have said wrong variable. V to the negative 1/2, u to the 1/2. Okay, and let's go ahead and find the determinant. So we're going to have negative 1/2 times 1/2, which would be negative 1/4. V to the 1/2 times v to the negative 1/2 would be v to the 0. U to the negative 3/2 times u to the 1/2 would be u to the negative 2 over 2, which is just u to the negative 1. Okay, minus 1/2 times 1/2 is 1/4. v to the 1/2 times v to the 1/2 would be v to the 0. And then u to the negative 1/2 times u to the negative 1/2 would be u to the negative 1. So we get u to the negative 1 and v to the 0 power. V to the 0 power is going to be 1. So we're going to have 2 of these negative 1/4 u to the negative 1/2. So 2 over 4 would be 1/2, and then u to the negative 1/2. And that's our Jacobian. We do need to put it in absolute value. So we put our absolute value bars around this. All right, so when we look at the double integral over the region R of xy dA, that's going to be equal to the double integral, and v is going from, it looks like we're going to change the order. It doesn't matter if it's uv or vu. It looks like I'm going to do u first, so 1/2 to 1, and then 1 to 2 for the v. E to the xy is equal to v, so e to the v, and here's your Jacobian. Absolute value of negative 1/2 u to the negative 1/2 dv du. So slide out the 1/2. Integral from 1/2 to 1. Integral of e to the v with respect to v is just e to the v. And then we also have the u to the negative 1 there, which we can rewrite as 1 over u. Evaluating v from 1 to 2 du. So that's going to give us e squared minus e to the first times 1 over u, so we can slide out the e squared minus e to the first out of the integral. Then we have the integral from 1/2 to 1 of du over u. So we have e squared minus e over 2 times the natural log of the absolute value of u, evaluated from 1/2 to 1. Okay. The natural log of 1 is going to be 0, so we'll just have minus the lower limit minus the natural log of the absolute value of 1/2. So you have e squared minus e over 2 times negative natural log of 1/2. We don't need the absolute value. Okay, you could distribute the negative sign there and make that e minus e squared over 2 natural log of 1/2. So you can also write it that way. Okay. Alrighty, so that's it for this section. This is our last section in Chapter 5. So we'll be getting into Chapter 6. So we'll see you next time.